Yeah, so we're going to do, I'm going to go over the daily 2 today, then we're going to do test corrections. And then I have a little bit of, I get to present about the 3 ways to charge objects, and then the electric force, which is known as Coulomb's law. And any time left, we're going to work on the I sure get a charge out of physics sheet in breakout rooms. Okay, so that's the plan for today. All right. So let's go over the daily 2. So I'm going to share the screen. And the first one looks like this. The objects become charged due to the movement of, and the choice and the correct response is electrons. Okay, protons cannot move because they are locked in the nucleus. I'm going to say that again and again and again. All right, so objects become, if an object acquires an excess of electrons, then it becomes negatively charged. If it loses electrons, it becomes positively charged. Okay, all right, that's the answer to number 1. Number 2, the energy of a mechanical wave depends on its amplitude. Think of a tsunami versus a ripple on a pond. Okay, so those are the 2 for today. Questions, comments on that? All right, let's go to the daily 2 from Wednesday. All right, so we have 2 blocks of iron, one having a mass of 120 kilograms. So they're 250 kilograms are on a table. Centers are 1.5 meters apart. What is the gravitational force of attraction? All right, I'm going to stop sharing and we're going to do this together. All right, so here's our data, and we want to know what the force of gravitational attraction. So we're going to use Newton's law of gravitation, cap G m1 m2 over r squared. And cap G, 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, times 1 mass being 120 kilograms, the other mass being 250 kilograms, all over 1.5 meters squared. And if you entered everything properly, okay, the answer was 8.9 times 10 to the, that part I forgot, 8.9 times 10 to the, oh gosh, 8.9 times 10 to the negative 7 meters. Okay, now I saw a number of responses, 1.3 times something. Okay, those of you who did that, I believe you forgot to square the 1.5 in the denominator. Okay, I think that's what that issue was. All right. Okay, so that was number 1, was law of gravitation. Number 2 was confusing to people, so I want to go through this. It said the weight of an object can be found by mg, where the mass of the object is cap m. Now, weight comes from gravitational force. So, for example, the weight of this mouse, let's call it cap m. All right, the weight of it can be found from mg, but weight comes from gravitational force of attraction between this object and Earth. All right, so we could apply Newton's law of gravitation to this, where cap m, that's m1, m2 would be Earth. And the distance apart is from the distance of the Earth's center to the location of the mouse, which is on the surface. So this is going to be the radius of Earth squared. Okay. All right. Oh, incidentally, I hope you enjoyed those center of mass demonstrations that I showed you on Wednesday, and I hope you did a bunch of them yourself. Okay. It's kind of fun. So we could treat all of the mass of Earth to be located at a single point in space, its geographic center. And so the distance from there to the surface is Earth's radius. Now we know so what we're going to do is we're going to set the weight equal to the force to the gravitation force. So we're going to set mg equal to g cap m1, mass of the Earth, divided by the radius of the Earth squared. Notice that the mass cancels out. Okay, the mass of the object, in this case the mouse, or you, or anything, they cancel out. And so what it gives us is that little g is equal to cap g, mass of the Earth, divided by the radius of the Earth squared. Now all these are constants, so we can plug these in. So we get G, 6.67. I'm going to move this up here. So G equals cap G, 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared times the mass of Earth, 5.96 times 10 to the 24 times 10 to the 24 kilograms, okay, over the radius of Earth, 6.37 times 10 to the 6 meters, square that. And if you enter all that into your calculator correctly, the number that comes out is 9.80 to 3 sig figs. All right, units wise, this meters squared cancels out that meter squared. A kilogram here cancels out one of the kilograms there. And if you remember what a Newton was, it was a kilogram meter per second squared. That's how I defined it. That's going to cancel out that other kilogram. And the unit that's left is meters per second squared. Okay, and that's gravitational acceleration. Way back when I just said, well, just trust me that it's this, and I'll show you where it comes from later. Here's where it comes from. Okay, it comes from Newton's law of gravitation. For the moon, if I plugged in the mass of the moon and I plugged in the radius of the moon in there and crank it out, it's going to be about 1.6. That's the gravitational acceleration on the moon. If you did it for Mars, put in the mass of Mars over the radius of Mars, you get about 3.7. Okay, for Jupiter, I believe it's 24.2. It just depends on the mass of the body and its radius. Okay, that's going to give you the value of gravitational acceleration for that body. All right, so that's where this actually comes from. Okay. Okay, questions, comments on that? All right. Well, now collaborative test corrections time. We're going to do this for 20 minutes. So it's 9:01 now. I'm going to create breakout rooms. Okay, I'm going to pause recording. I will take you can submit them to Schoology again, or you can email them to me, either one. You can send me that. And I'm going to give you till the end of today, all right, to get that in. And then I can, I will award you points for making those corrections. All right. So let's move on. And what I want to do now is get back into that PowerPoint, and I want to talk about the 3 ways that you can charge objects, okay? You can put it right, you can send it, a couple questions. You can send a Schoology right back to the same place, just put it as revision 2, all right? Or when in doubt, just email it to me, okay? And I can just, I'll have them on separate tabs, and I can just compare them that way, all right? Very easy for me to do. Okay, and so the 3 ways to charge objects. So I'm going to share the screen, and we're going to go through that PowerPoint lesson again for a little while. But before, let's talk about what we did last time, from results from the electrostatics lab that we did the other day. What we did, one of the things we did, was we brought a negatively charged strip or ball or a rod near a neutral ball. Okay, so on the ball itself, the electrons were repelled to the far side of the ball. Okay, and and then, overall the ball was neutral, but the electrons were on the far side. There's a repulsion between the negatives, and there's attraction between the positives and negatives. The attraction wins because they are closer. So the ball moved to the rod until they touched, and then electrons moved from the rod to the ball. Okay, and then they became both negative, and so they repelled each other. This also happened when we use a positively charged rod. In this case, it wasn't that the positive charge was, if this were a positively charged rod now, okay, let's pretend that. As I brought it near, I could say that the protons were repelled to the far side, but that would be wrong because the protons are locked in the nucleus. Instead, electrons are attracted to the near side. Okay, and then the positively charged rod would attract the electrons more strongly than it would repel the protons. And so once again, we get a net attraction until they touch. And in this case, electrons would move from the ball to the positively charged rod. Okay, since electrons left the ball, it becomes net positive, and so again, repulsion occurs. Okay, so the new thing from this year is that charged objects will attract neutral objects until they touch. Okay, then charge transfer will occur, and then it will acquire like charge. Okay, this is actually one of the ways that it is to charge an object, and I'll document that shortly. All right, now one way to charge an object is by friction. Just when I rub that plastic rod with fur, I literally ripped electrons off the fur, depositing them on the plastic. This is what happens when you walk across a carpet. Okay, you scuff your feet along the carpet, ripping electrons from the carpet and placing them on your body. And you can get charged up to the point where if you try to touch a doorknob, you can get a spark. That's annoying. That hurts. Okay. And that's one way to charge an object. Okay. The second way to charge an object is by conduction. By conduction. Okay. And so let's say we have a charged object, and let's say it has a charge, a positive charge. And in physics, we represent charge with the letter Q. All right. So this ball has a charge of positive Q. This ball is neutral. All right. Now let's pretend just for a minute, for ease of discussion, that positive charges can move. Okay. Yeah, we know they can't, but let's just assume they can, just to make the discussion a hair easier. Let's bring them together. Now, when they touch, charge transfer will occur. Okay. And these positive charges will distribute over the second ball. Okay. And if the balls are the same size and of the same material, okay, then they will split the charge evenly. Okay. So if this ball started out with positive Q, you'd end up with Q over 2 here and Q over 2 here. Okay. They split the charge evenly. All right. And this is charging by conduction. Okay. And it involves contact, and it acquires the same charge as the charging object. All right. And this is what happened in our lab. Okay. When we did that, just being a little redundant here, charge transfers occur, electrons transfer to the sphere, and the sphere is negatively charged. Okay. That is charging by conduction. Okay. So we have friction and we have charging by conduction. Conduction meaning touching. Okay. There's another way to charge, and that's called charging by induction. Okay. Now, the root word of induction is induce, and that means to force to happen. So charging by induction is when we force charges to move around. Okay. For example, let's say we bring a negatively charged strip near a neutral ball, near but not touching a neutral ball. As before, the electrons on the ball will be repelled to the far side. Okay. Now what we do is we ground the ball. This is a symbol for ground. We connect it to the ground, either by touching it with your finger or by literally connecting it with a wire to the ground. Okay. Now, when that happens, the electrons that are repelled on the far side, being repelled by the negatively charged strip, they see an opportunity to get even farther away from that negatively charged strip. And so they leave. They go into the ground. Okay. They exit the system into the ground. All right. Now we break the ground connection first. Okay. We break the ground connection, and then we take the strip away. Okay. Now it's important that you break the ground connection first. If you took the strip away, all right, then the inducing force is gone. The electrons will come right back out of the ground to make the ball neutral again. But if you break the ground first, then they cannot get back in. And what you're left with is a positively charged ball. Okay. So we used a negatively charged object, and we end up with a positively charged ball. Okay. If instead we had used a positively charged strip, then the electrons would be attracted to the near side. So let's pretend this has a positive charge now. The negative charge is attracted to it. Then when we connect it to the ground, which is an unlimited supply of electrons will actually come out of the ground being attracted to the positively charged object. If we then break the ground connection, the electrons are trapped inside the ball. Okay, and then we would end up with a negatively charged object. So this is charging an object by forcing charge to move around. Okay, all right. Now,
Can you give us a sec to write that down?
yeah. So,
See?
question?
So when the connection to the ground is made, and electrons are repelled into the ground, the ball doesn't lose electrons into the ground.
Yes, it does.
So where does it get the other protons from?
These protons? Well, they're just more electrons left the ground. More electrons were repelled away. Okay, maybe I should have only had 2 positive charges on my belt.
Oh, okay.
Okay, maybe I should have. Maybe my diagram is a little unclear. Maybe I should have left it with only 2 positive charges, being those 2 positive charges. Yeah, that might have been a little clear. So sorry about that. Sorry about that part. But electrons are repelled into. They literally go in. They're dumped into the ground. Literally. Okay. All right. The ground can be an unlimited supply or an unlimited sink for electrons. Okay, they literally travel into the ground. And then if you break that ground connection, they can't get back in. So we're left with an overall positive charge. All right. Now, charges are very, very small. But I do want you guys to have an idea or be able to tell me how charges move around in a system. So you need to know the rules for charge movement. However, that's the bad news. The good news is they're very simple. Okay, there are 3. Oops, I forgot to mention. I forgot to put this on. It induces charge movement and acquires charge opposite that of charging object. I'm not really going to test you on that stuff necessarily, but I do want you to know how charges move around. Okay. Oh, by the way, this PowerPoint presentation is loaded on Schoology. You can get it. You can print it out if you wish. All right. The rules for charge movement. There are 3, and they're simple. Number 1. Electrons move, not protons. Protons are locked in the nucleus. It's only the electrons that move, okay? Okay, rule number 2. Electrons move away, are repelled from a negative charge. And rule number 3, electrons move towards a positive charge. Those are the rules for charge movement. Simple. It's the electrons that move, and they're repelled from a negative, and they're attracted to a positive. Okay, if you know those rules, you will be able to be successful. You will be successful in doing the exercises that I would like you to do. Okay. All right. So give you a moment to write those down, and then we're going to do such an exercise as an example of what I would like you to be able to do. All right. So I'm going to stop sharing. Okay, so what I have here are 2 spheres. All right, they're ping pong balls that are glued to a wood stick, and I covered the ping pong balls with foil. Okay, in case you care. One of them is banded with blue tape. Okay, now what I'm going to do is I'm going to charge up. What kind of charge does this have?
Neutral.
This? After I rubbed it with fur? No.
Oh,
Okay.
after.
After I rubbed it with fur, like this.
Negative.
Positive or negative?
Negative.
Negative, correct. I ripped electrons from the fur, placing them on the plastic. Yeah. Okay. So I end up with a negatively charged object. All right. I'm going to have these 2 spheres. These 2 spheres are neutral. Okay. They're neutral. All right. They're touching. What I'm going to do, this is really a 2-person exercise, but. All right. So I'm going to bring a negatively charged object near that side. And while it's near but not touching, I'm going to separate the spheres. Okay. What are the charges on the spheres? I'm going to call this sphere A, this sphere B. Oh, I can stand this thing up. Okay, well, I can do that. All right, do this again. So sphere A, sphere B. I'm going to hold it near but not touching. And I'm going to separate them. Okay. What are the charges on these? Okay. Pictorially, I'm going to represent it like this. Bring a negatively charged object near two connected metal spheres that are neutral, sphere A and sphere B. While it is being held near but not touching, I'm going to separate the spheres. And then I'm going to take the object away. What is the charge on each sphere? Okay. What is the charge on sphere A? Positive, negative, or neutral? And what is the charge on sphere B? Positive, negative, or neutral? All right, make a prediction. Now, does anybody want to share their prediction? Would anybody like to share? A positive, B negative. That's correct. Yeah, good job. Yeah, awesome. Because the negatively charged object, let me stop sharing. The negatively charged object on the rod will repel electrons away. Neutralize them again. And so the negative charge on the rod will repel electrons away onto this sphere. Oops, I touched it. Shouldn't have. Oh. Yeah. And then if I separate them, I trap the extra electrons over there. And the electrons that left this is going to leave this, is going to render this positive. Okay. All right. Now, let's test this to see if it's true. And this may or may not work. Electrostatics demonstrations are really tricky. You don't know. I never know whether they're going to work or not. I just keep trying and trying and trying in the hopes that they do. So I hope this does, but I can't guarantee it. So I'm gonna use my little thing here as a tester. Okay, so I'm gonna the one with the blue band, I'm gonna charge negatively. Okay, that has a negative charge on it. All right. And I'm going to try to put a positive charge on the other one. Good, solid positive charge. All right. Okay. All right. So I have positively charged balls and negatively charged balls, and I can use that as a tester. Now I'm going to do a little exercise with the spheres. Get a good negative charge on that. Near but not touching. Separate them. And we said A should be positive, so it should repel that. And no, sure enough, it doesn't. But maybe B, I can show B to repel. No, it's just that I can't get, when I used to have plastic strips instead of round rods, I had more surface area closer to the ball. I just had this little tiny, and that's my problem. I know is I got to buy some plastic strips instead of using PVC pipe. So I can't show this, but you were right. You were right in that the sphere A would be positive and sphere B would be negative, okay? So apply the rules of charge movement to imagine and tell me which way charges move around the system, okay? Sorry that I can't show that to you, but it's just, I don't have the proper equipment for it. All right, next is something called, question.
Before we move on, going back to the induction.
Yeah.
When there's when there's the ground, so that's kind of like an unlimited supply of electrons.
Yes, or an unlimited sink. You can dump as many as you want into the ground, or you can get as many as you want out of the ground. Yes.
So, for example, if there was a neutral charged ball or like a positively charged ball, and it was connected to the ground, would electrons want to go into it and make it neutrally charged and make it just neutral?
Yes, and that's what happens if one of these balls is, let me stop sharing for a minute. If this thing has an excess of negative charge, okay, and I touch it, that negative charge goes into my finger. All right. If there's a deficiency of negative charge, that is, there's more positive charges than negative charge, it's positively charged. If I touch it, then electrons come out of my finger to neutralize it. So yes, I can be considered a ground in this sense, at least. Okay, there's an unlimited supply or an unlimited sink for electrons, me or you.
Oh, and Mr. Tauges,
Yeah,
just to be clear, the apparatus that spins, it spins because each positive side is chasing the other negative side.
it's more for being repelled. All right, so
Oh, okay.
so attraction is not a valid test for charge unless you absolutely know that the object is charged. If you know an object is charged, but you just don't know which charge it is, then you can use attraction or repulsion. If you don't know whether an object is charged, you can't use attraction because it could be neutral, right? Neutral objects are attracted to charged objects. So for that test, you're really looking for repulsion as the valid test. So if I have this, if that repels it, and it does, still has okay, let me put a negative charge in there. Okay, if it attracts, then I don't know. It could be neutral. But if it repels, then it's most definitely the same charge. Okay, so it spins. So repulsion is the valid test. Yeah. Okay. Other questions? All right. There's a Frenchman a few hundred years ago by the name of Charles Coulomb, and he did experiments with charge. Okay, before they ever really knew what charge was, right? They did experiments. He knew he could place. You could rub something with fur, and for example, like this, you could deposit charge. So he knew this object was charged. Didn't know what charge, what it was. Didn't know how many was on there, but he knew it was charged. And he took a neutral one and he touched them together. And he split them up. Now they know they had the same amount of charge, same size, same thing. Okay, they split the charge evenly. So whatever charge was on here, okay, he could split it up and split it evenly. Okay, and then he could have 3 of them, and so they would split it into thirds. He could touch one, neutralizing it, and then touch it again. And now the half would be split again and have a quarter. So he could get the ratio of charges on different objects. Okay. And then what he did was he measured the force between them, the force of attraction or repulsion. Okay. And he did a whole bunch of experiments before they even really knew what charge was. This was in the 1700s in France, right around the time of the French Revolution, probably, maybe a little bit before. Okay. And he came up with something called Coulomb's law. All right. And I'm going to show that to you. All right. Getting past here. Coulomb's law. Now, here's the English. You do not need to write down this English. The force, but here's what it is. The force between 2 point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. That is, when the charges went up, the force went up. When the distance went up, the force went down. By the square of the distance. Okay, you don't need to write down this English, but write down the mathematical equivalent. This is Coulomb's law. Okay, for the electric force. All right, I'm going to write this on the board. The electric force is equal to K Q1 Q2 over R squared. Now, what do these represent? Q1 is the first charge, Q2 is the second charge, R is the distance, and K is a proportionality constant that had to be measured. And it was measured, and it turned out to be, to have a value of 9 times 10 to the 9 Newton meter squared by capital C squared. Now, capital C is a Coulomb, because they ended up naming the unit of charge after the guy. There he is. Okay, he lived in France in the 1700s. Okay, and the unit of charge. Now, he did his work in the 1700s, long before they knew what charge was. It wasn't until the latter years of the 1800s, over 100 years after Coulomb did his work, that the electron was discovered by an Englishman by the name of J.J. Thomson. He discovered and named the electron in 1897. The charge on the electron wasn't measured until almost 20 years after that, in 1915, by an American by the name of Robert Millikan. And one of the most famous experiments in physics history. It's called the oil drop experiment. He measured the charge on an electron. And as it turned out, it's this, negative 1.6021 times 10 to the minus 19 of a Coulomb. Write that down, please. Okay. Once they figured out the charge of the electron, they knew the charge on the proton. It's the very same, just positive. 1.6021 times 10 to the minus 19 of a Coulomb. Okay. Okay, I would like to use Coulomb's law. I'd like to do an example with Coulomb's law. You will find this example in the example in this week's Schoology folder. I'm going to stop sharing and show you this. If you let's see here. In this week's Schoology folder, I can't minimize this because I'm recording. If you go to this week's Schoology folder, you will find a document called Coulomb's Law Examples. Okay, and the first example looks like this. Oops, now I do have to share. Excuse me for a minute. The first example looks like, I got to get out of here. Well, actually, the first example is in here. Find the force between charges of positive 2 coulombs and negative 3 coulombs located 1 meter apart in air. I want to do this example. I'm going to stop sharing in a minute, but I'm going to write this stuff down. Q1 is equal to positive 2 coulombs. Q2 is equal to negative 3 coulombs. They are separated by 1 meter. All right, and I want to find the force. Okay. Okay, I'm going to stop sharing because it's in here, but I'd rather do it on the board with you. Okay. You will need the value of the constant K, which is the electrostatic constant, 9 times 10 to the 9. Easy to remember. 9 times 10 to the 9. Newton meter squared per Coulomb squared. Okay, let's use this data and put it in Coulomb's law. So Coulomb's law for the electric force, K Q1 Q2 over R squared. All right. Okay, copy step. K 9 times 10 to the 9 Newton meter squared per Coulomb squared. Okay, Q1 positive 2 coulombs. Q2 negative 3 coulombs, and they are separated by 1 meter. All right. Now, get out your calculators. Enter that into your calculators. Okay. And if you do, and you do it successfully, well, let's worry about units for a minute. Meters squared is going to cancel out the meter squared. Coulomb times a Coulomb is going to cancel out Coulomb squared. And you're going to be left with newtons, all right, which is, of course, the unit of force, all right. And then if you do this, if you enter this into your calculator correctly, you will get an answer of 5.4 times 10 to the 10 newtons. 5.4 times 10 to the 10 newtons. All right. Now, if I wrote this out, what is this? Big force, small force, medium force? Well, if I wrote this out, look at this. 5.4, 10 decimal places. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What do you think? Big force, small force? That's a huge force. I mean, if I did old style and put commas in here, that's 1,000 million, billion, 54 billion newtons of force. Now, that's ridiculously large. Okay, so if I put if I put, oh, by the way, I forgot something. Before I talk about how big it is, I forgot the negative sign. It's negative. Because one charge is negative and the other one's positive. So the negative here. Now, in physics, oftentimes we use negative signs to indicate direction. You know, negative signs moving to the left, you know, or down perhaps, but not here. And we have Benjamin Franklin to blame for this, because he's the guy who said, hey, let's call them positive and negative charges. And everybody says, oh, okay, that sounds like a good idea. Well, maybe not so much, because this negative sign does not indicate direction, okay? It indicates attraction, because one charge is positive and the other one's negative, and those two attract each other. So this negative sign really means attraction. And this has caused confusion in the past. And again, we have Benjamin Franklin to blame for that, first great American scientist. But I kind of wish he hadn't done that, because it it helps in other ways. But so this negative sign does not indicate direction; it indicates attraction. Now, what about a positive? We have two positive charges. Positive times a positive would end up with a positive force, and that's repulsion, right? Or a negative times a negative. You also get a positive force, which indicates repulsion. So a positive force indicates repulsion, and a negative force indicates attraction. It does not indicate direction. You got to be careful about that. Okay. Okay. Secondly, this is an enormous force. If I put 2 coulombs of positive charge, or this was positively charged 2 coulombs, and this was negatively charged 3 coulombs, and I held them a meter apart, which is like this, they would attract each other with 54 billion newtons of force. There's absolutely no way. You know, I like to think of myself as strong, but I'm not 54 billion newtons strong. No, I couldn't hold them apart, not even close. All right. Now, why did it turn out that way? Well, because they defined the coulomb back in the early 1800s when they actually defined it using electric circuits, which we'll talk about later. Right, and they kind of got it wrong. They put too much charge in a coulomb, by a lot. You know, I mean, the charge on an electron. Remember what the charge on an electron was? 1.6021 times 10 to the negative 19 of a coulomb. That's a billionth of a coulomb. Okay. Now, when Millikan measured the charge on an electron, they said, whoa. Boy, that coulomb was kind of misdefined 100 years ago, right? They made it way too big, right? But they said, we're not going to undo 100 years of physics. We'll just leave it like that, and we'll just understand that a coulomb of charge is a tremendously large amount of charge. If there was a coulomb of charge on this ball, I wouldn't want to get anywhere near it, because it'd be extremely dangerous. Okay, there's no way we can get a coulomb of charge on things. There's just no way. At least I can't, not with the stuff I have. Much more typical of the charges that build up on things, like when you scuff your feet along a carpet, or maybe clothes in a dryer, they come out all staticky. A much more typical charge is a millionth of a coulomb. That's much more typical of the ones that we see in everyday objects. Okay. So I want to do an example of that, because that's the charges that you will see in problems, okay? And so I want to do example number 2. So if you'll check out example number 2, let's see. Oops. So I go through this. Negative sign indicates attraction. I want to do this one. Now, I'm going to stop sharing for a minute. I want to define a millionth of a coulomb. This is much more typical of the ones you see in nature. Okay, and a millionth is 10 to the minus 6. 10 to the minus 6. 1 times 10 to the minus 6. Zoom in a little bit. Okay, and 1 times 10 to the 6 is called a micro coulomb. Micro is the prefix for 10 to the minus 6. Okay, 1 microcoulomb is 10 to the minus 6. And the symbol for a microcoulomb is a Greek letter mu. Okay, it looks like a funny U. I may have mentioned it back when I talked about the coefficient of friction, because it also represents the coefficient of friction. But in this case, it represents a microcoulomb. So 1 microcoulomb is 1 times 10 to the minus 6 coulombs. And these are the charges that you're going to see in everyday problems. For example, example number 2 in our example sheet, okay, which looks like this. A charge of -3 microcoulombs exerts a force of positive 1.5 newtons when separated by a distance of 0.4 meters. What is the sign of the other charge? Okay, let's do this together. So, example 2, Q1 is equal to -3 microcoulombs. Okay, and now I'm going to stop sharing. Okay, and whenever you see a microcoulomb, just immediately convert it to coulombs, because you're going to have to when you put it in Coulomb's law. Okay, microcoulomb is 10 to the minus 6. Okay, the force was positive 1.5 newtons. What we want to know is, part A, what was the sign of the other charge? Sign of Q2. Is it positive or is it negative? Well, it's a positive force. Remember, a positive force is repulsive, okay? Positive force indicates repulsion. And if the first charge is negative, then a positive force, which indicates repulsion, means that Q2 is negative also. All right? Q2 is negative. Okay? All right. Part B. What they want is the magnitude of Q2. What is how many coulombs is Q2? To solve this, we need to take Coulomb's law. F is equal to KQ1 Q2 over R squared. And I need to solve this for Q2. I need Q2 equals, right? Now, once again, I'm not going to put the numbers in right now because then I'm just going to be writing too much. Instead, I'm going to solve for Q2 first. That means I'm going to get rid of the R squared. How do I get rid of the R squared? I multiply by it. And when I multiply by it, it cancels out over here. And all I'm left there is KQ1 Q2. Over on the right, I have R squared F. Okay, remembering that I want to get Q2 all by itself. That means I got to eliminate the K and the Q1. And I can do that by dividing. Everything cancels out over here except for the Q2. Q2 is equal to R squared F over KQ1. All right, now I have everything solved for the equation solved for Q2. Now I can plug my numbers. So there was 0.4 meters of distance between them. I did not write that in my data table. Should have wrote that in my data table. R is 0.4 meters. Square that. The force was positive 1.5 newtons over K, 9 times 10 to the 9 Newton meters squared per Coulomb squared. And then Q1 was -3 times 10 to the -6 coulombs. So I get -3 times 10 to the -6 coulombs. All right, units wise, meters squared cancels out that meter squared, newtons cancels out the Newton, Coulomb cancels out one of those. I'm left with the Coulomb in the denominator of the denominator, so it comes back on top. And then the number, which I've forgotten, so I'm going to crank this out. Equals divided by 9, 3, 5, 6. And I get, oh yeah, I remember now. I get 0 point. Wait, how many zeros are there? 1, 2, 3, 5 zeros. And then a bunch of 8s ending in a 9. So I'll just use 2 sig figs. So 0.00000089 coulombs. All right. Putting this into scientific notation, 1, 2, 3, 4, 5, 6. This is going to be 8.9 times 10 to the negative 6 coulombs. And remembering that 10 to the minus 6 is a microcoulomb, I could also write this as 8.9 microcoulombs. I would take any one of those 3 answers as correct. Okay, so these are the types of charges that you will see in real life problems. Okay, in real life problems, you're not going to see a coulomb of static charge on an object. It's just not going to happen. Okay, not without special equipment. Okay. All right. Now, don't really have time to bust you up into breakout rooms, but next Tuesday, I'm going to give you guys about 25 minutes maybe to work on I Sure Get a Charge Out of Physics. Okay, that's going to be due at the end of the day, Wednesday. All right, but I'll give you some time. Now, there's 12 items on there. 25 minutes might not be enough time to get it all done. And there is still a couple of things that I want to do with Coulomb's law that I don't have time for, which I will do on Tuesday. So I'm going to finish up Coulomb's law. Then I'm going to send you guys breakout rooms to work on I Sure Get a Charge Out of Physics. And then I'm going to bring you back and we're going to start talking about electric fields. Okay, got a lot of pretty cool, fun demonstrations to show you. And I'm pretty confident those will work. The electrostatics ones, they're just tricky. But the electric field ones work a little bit better. Okay, questions, comments for me? Questions, comments for me?
Does the unit of coulombs, does that matter if that's a capital or
Yes.
non?
Good question. Yes, it has to be a capital C, okay? Because lowercase c represents probably the most important number in all of physics and therefore all of nature, the speed of light. So there's a very big difference between little c and big C. Yeah, the Coulomb, the big C is the unit of charge, which is one of 7, incidentally, one of 7 fundamental units in physics. Okay, meter, second, gram, liter. No, not liter. Coulomb, candela, representing electric light intensity, the mole amount, and the Kelvin, which is the unit of temperature. Those are the 7 fundamental units. All other units are combinations of them. But so I probably told you more than you needed, more than you wanted. But yeah, capital C, it has to be capital because lowercase c is the speed of light.
Could you briefly go back to problem 2, letter A? The
Letter-
sign of other charge.
The sign of the other charge. Okay. The sign of the, how do I know that Q2 is negative? Because it was a positive force. Okay, and a positive force indicates repulsion. Okay, and
Meaning
so
it had to be to the same charged.
Yeah.
2 of the equal charges, or not equal, but 2
Like-
negatives or 2 positives.
yes, like charges.
Got it.
Like charges. If Q1 is negative and it's a positive force, that means the other charge is negative also.
Okay,
Yep.
so we'll always be given one.
In this
Positive
type
force.
of problem, yeah,
Got it. Or not force is one of the charges.
in this, yeah. Mhm. Okay, other questions? All right, then, we have reached